Okay, good afternoon, morning, evening, everybody. And my name is Federico Fierli. And on behalf of EUMETSAT, I welcome you on this fourth short course. We have a series of short courses that happen almost every 2 weeks. And for the session today, you will see we will focus on one of the images that you see here. So we'll discuss about fires. But before going in the session, there are a few technical issue. So the first one is keep your video and audio off, because with a quite a large number of participants, it is difficult. It can become difficult. But in order to exchange your feedback, ideas, questions, you can use Slido. So go to slido.com, and then you can make use of the event code EUMETSAT. And here is for any questions you want to make to the speakers, to myself, and we will do our best to answer to all of them before the end of the session. While if you have technical issues, you can make use of the chat box, of the Zoom chat box, and writing to support. So you choose a support here in the list of participants, and then you ask to support if you have problems, for instance, with connection and so on. Otherwise, you can you can use the chat to talk among you, and also to greet and to interact. So let's go in on the core of our session today. Okay. First of all, I just want to give you a couple of words on what is EUMETSAT. Probably most of you are aware of what EUMETSAT is, but nevertheless, EUMETSAT is an international organization that is participated by most European countries, and our work, our mandate is to monitor climate, weather, environment from satellite, and we do this for Europe and worldwide. To do so, we manage and we follow a series of satellite programs. Among them, you have the METOP, so meteorological operation satellites that run on polar orbits, the METOSAT, and for them there are both present and upcoming generation. One new thing that is coming out is also the monitoring of the CO2. One of the big things that we do in EUMETSAT is also to support the Copernicus program. Copernicus is the European Commission cornerstone program for Earth monitoring, and one of the part of the Copernicus, one big part of the Copernicus, is the development of the so-called Sentinels. Sentinels are a series of satellites that are partly in orbit and partly are closer to launch, and other are planning. For instance, Sentinel-6 is planned in a few days, while the Sentinel-1, 2, 3, that is the object of discussion today, and 5P are already operating. These satellites provide the most advanced datasets as possible for Earth monitoring, and they are totally free of use. And they will be one of them will be object of the today talk. What we also do, and we try to make data available at best, and then we gather and try to satisfy needs. We grant the data access, we have help and support the user, and we do training also online. And this is part of this activity. Okay. I'm sorry, it is blocked. I go in that way. So today we talk about fires. The title is a bit slightly changed with respect to the first announcement, because it has to reflect what has happened in the meanwhile. So we will talk about summers of fires, summer in the boreal and northern and southern hemisphere. So we will see how with satellite we will measure wildfire in Australia, Siberia and California. And we have Julien Chimon, who will provide the first talk on measuring fires and pollutants. Julia Wageman will drive you on the data discovery, and then we will have a session on wrap up. This is the program for today, but the course does not end today. There is a self-paced phase that will last until the 19th of October, where we will have a feedback session, same time, so 12 UTC or 2 Central European Summer Time. And in the feedback session, we will be able to support you with the questions, with the activity that you have had during the week in discovering the data by yourself. Everything about the data is here, is available on the course webpage. So we invite you to go on the course webpage where you have all the links and all the indication on how to download the data. You already have received by email the indication of this. So in that way, you may be able to also to follow Julia today and to prepare to make your own data analysis for the next session. Again, the discussion is on Slido with the code EUMETSAT, and please provide question. I remind you that any question is good. I mean, it's not a question of quality. Just some advertisement. We have an upcoming course. This is a longer course. It will last 1 week and is organized by ourselves, by European Space Agency, and by European Center for Medium Range Weather Forecast. This is the second edition of a school. The first one we had it last year in 2019. It was on site, and this one is fully online. But the aim of the school is to support you in developing a small project, to have data handling, to discover many other data with respect to what we can today in a short and focused course, and also to have inspiring lectures from top-level lecturers. So the applications are still open. They close on October 20, so there is 1 short week to apply. And in order to apply, you just go on the webpage www.atmostraining.info, and you will find all the information there. So please come there, or also come back to us if you need additional elements. I will introduce now the presentation, the first presentation from Julien. I mean, the question is why we talk about wildfires. So wildfires are a key issue because on one side we are in a hotter and drier world, and you see here the increase that this is a quite recent Nature communication papers that, I mean, based on satellite data indicates that there are longer fire weather conditions from during the last 2 to 3 decades. So there is an increase of the period when it is possible to, of course, to have wildfires. The fires, they impact on the climate, and I won't waste time, but here in the slides you will find a link to a NASA carbon emission video showing that they play a lot in terms of emission of aerosol and the carbon species. Of course, there is a human factor. This is an image of Amazonia, but the way that the human they make use or they manage the land has a big impact on the wildfires, and vice versa, of course. And also we have fires feedback, and one of the main feedback is on health, and is on health, on security, and you see here this is an iconic image of the Golden Gate after the huge fire in California this year. Satellites are important, and this is why we make this course. Satellites are a privileged observatory because they allow many things, and our objective is that you are able to do as well many things with the data. So, for instance, it is possible to to monitor, identify the fires in near real time. So this is an image from Sentinel-3 of the visual plumes. So this is again California, and this is an example of the detection from the Sentinel-3 fire radiative product, near real-time product that you will see today on the fires in a single snapshot. Then satellite can be used to understand and to evaluate the extent and the impact of events, and that this is again the case of California with this huge aerosol plume that is transported towards Europe. And here you see the same plume on Northern Europe. And then you can also, thanks to the global and continuous record, also to establish trends. And for instance, this is one of the big puzzles that we have on the climate side of the fire. So based on the data until 2005, for instance, there is in fact a decrease of the burnt area, but it seems that there is an increase of the intensity and severity of fires. So it is also a very important and open issue in terms of climate variability and overall impact. But I mean, I close here, and I leave the floor first of all to Julia Chimot from EUMETSAT, and then to Julia Wagaman. Then, just a quick reminder: please go to Slido, put questions, and enjoy the course. If there are some burning issues, some burning questions that you would like to see solved, also put them in the chat, and we will try to convey it to the lecturer. Thank you very much, and enjoy our course.
Thank you, Federico. Good afternoon, good morning, good evening, everyone. I'm very happy to be with all of you for this course about fires during summer 2020. So I'm going to share my slides with you. You should be able to see them. If not, I guess one of you will stop me. So as Federico said, I am Julien Chimot. I'm working at EUMETSAT, and my work is about basically measuring fires and pollutants, all of them at any time. But of course, during that course, I will focus about the summer of 2020, and I will try to give you a bit of hints on how we measure fires, how we measure pollutants, and from Sentinel-3, because my core job is actually on Sentinel-3. Before going to some details and information, I will invite you to fly a little bit with me and with Sentinel-3. Yeah. Okay, so if you fly with Sentinel-3 and you open a nominal picture, typically last summer, this is firstly what you will see with your own eyes. So it's quite straightforward. You mostly see clouds, which are these white big patterns. You see vegetation in green. You see bare throws in yellowish or brown, and the ocean in blue. So these pictures, this is what we see every day with Sentinel-3. Is it a normal day? It's 19th of August. If you zoom in carefully, you will find out that this day was absolutely not normal. For example, here we are in Siberia, and you can see all this huge amount of smoke. So very harmless for all population. And it was because of fires that were ongoing during the whole summer in Siberia, because it was very hot and very dry. If you move to the US, here in California, you can see another thick smoke, a bit yellowish, brownish, again related to fires, but this time over California, which have been burning mostly from August to end of September. I think it's still a bit ongoing now, although it's much lower. But these were not the only fires ongoing this summer. We also had a lot of fires, unfortunately, in South America. This is what we usually call the Amazon fires. And also Central Africa. So on that day, it was a bit more difficult to see, but you can still guess it with your eyes. You have this thin layer of smoke mixed with clouds and mixed with a bit of dark vegetation. So clearly, not really a normal day if you compare with today. But of course, this is what we see with our own eyes. At EUMETSAT, we do not launch satellites like Sentinel-3 to only tell us something that we already know with your own eyes. We want to see a bit beyond that, beyond what is visible. If we go beyond that with all the processing chain that we have, this is what we can deduce. For example, for the same day, or I should say more by night, we can count the overall number of fires burning on that night and how powerful, strong they were. On that specific night, we had about more than 14,000 fires burning all across the world. You can see some of them in a reddish over Siberia, California, the Amazonia burning a lot, Central Africa, a bit of Australia, and so on. And also we can see that these 14,000 fires were really strong. We could estimate what we call the radiative power, so how powerful were these fires. And yeah, each of them were going much beyond than 50 megawatt, so it was pretty strong. But also beyond that, we could also interpret the impact in terms of air pollution. So here this is a picture which I will detail you a bit later on, which tells us the overall amount of particles released in the air. So we can see the particles released over California, over Siberia. This is mostly in red. If this is red, it means a lot of particles. If this is blue, it means almost very clean air. So yeah, you can see in red over Siberia, California, the Amazonia, the core of Amazonia fire was really burning a lot, releasing very unhealthy and harmful black smoke, and also a little bit of Central Africa. The other red, it's other types of particles like dust and so on that are not related to fires. So this is what we can see today from Sentinel-3 and what EUMETSAT is processing and making available to all of you. Now, how do we do that and why we do that and how we make them available? That's gonna be the core of this talk. So I'm going to talk about Sentinel-3, the link with Copernicus and EUMETSAT, which is a little bit what Frédéric already said. Then I'm going to introduce you about the Sentinel-3 near real-time fire data, then the Sentinel-3 near real-time aerosol data, and then I will conclude with some links about how to find this data, how to visualize them, and that we give the transfer to Julia with some demonstration. One first thing, I will say a lot during that talk, NRT. NRT stands for near real-time. It means basically that starting from the measurement time until you, as user, get the data, we do not exceed more than 3 hours. And in fact, you get the data between 2 and 3 hours. So this is what NRT or near real-time means. Okay, so firstly, Copernicus and Sentinel-3. So why we look at fires, Federico mentioned about this. An important component of fires is that it releases a lot of smoke, a lot of particles. In a scientific world, we call them aerosols. So aerosols are very tiny particles that fly in the air. They are really tiny, but we are able to see them from satellite measurements. They have various sources. Some of them come from deserts, others come from volcanic ashes, others come from sea salt when you have a huge storm and waves, and then you have a lot of sea salt spray splashing on your face or so on. Then we have a lot of industrial pollution releasing these particles. But on top of that, fires, especially during summertime, are an important source of these aerosols of tiny particles. And if these fires occur close to populated areas, then clearly we have to anticipate how it's gonna impact them and how much it can harm them. These particles have very variable variety of colors, size, shapes, chemistry composition, and they directly affect, of course, air pollution, but also the visibility. As Federico showed you in San Francisco, the California fires reduced all the visibility in the sky. You could not see the sky anymore. It creates a lot of pressures from climate point of view, and also can interfere with satellite information dedicated to other topics. So Copernicus, this is the European system. It's a directive funded by the European Commission for monitoring the Earth using satellites and in situ sensors. And EUMETSAT is one of the main partners of Copernicus. As Federico said, we have a huge fleet of satellites under development or already developed. We call them Sentinels. The already existing ones are Sentinel-1, 2, 3, 5 precursor, and very soon Sentinel-6. All of them are satellites. And in the future, we will have actually even Sentinel-4 and 5, which are more atmospheric dedicated instruments. The nominal routine of these Sentinels, once they are launched and everything is going fine, is operating between the European Space Agency and ESA and EUMETSAT. More specifically, we EUMETSAT, we operate directly Sentinel-3 4, 5 in the future, and 6 by operating. It means that the mission control center is actually based here in Germany at EUMETSAT. And the data that are derived from these satellites are totally free, fully and publicly accessible to any of you, as well as to big services that we call Copernicus services, in order to exploit them for further enhanced information. One of the main users of this data, this is what we call CAMS. CAMS, this is the Copernicus Atmospheric Monitoring System. It's basically the chemistry weather forecast. So you all see a meteorology forecast on TV for checking what will be the weather tomorrow. But on top of that, in Europe today, we also have the chemistry weather forecast to tell us how good or bad will be the air quality tomorrow. This is implemented and operated by the European Center Medium Weather Forecast, with whom we work every day. And many of these data are made available via your mobile or via different applications. For city and regional air quality services, you can also see the forecast on TV sometimes. And so basically, what you have at the end, you have the satellite measurements like Sentinel-3 that are acquired from space. These data, these measurements are dumped to Earth and then transferred to EUMETSAT. At EUMETSAT, we process these measurements to produce the maps that I showed you earlier. We make available these maps in less than 3 hours to all of you. We also make available these maps to CAMS, our partner, and then CAMS use this data to produce a forecast about the air quality of tomorrow and beyond tomorrow. So that's basically the chain. And all of this is done in what we call NRT, new real time, so less than 3 hours. One typical example of what is done with CAMS, at the top left, this is a typical fire product that is assimilated by CAMS. So these fires are estimated every day. Then they assimilate that in their own models, and then they deduce on the right the direct impact on the air quality. So in that case, this is a toxic gas that we call carbon monoxide, which is purely due to the fires. And then you can even go beyond on the bottom left. They can even forecast, because of the actual fires, what will be the impact in terms of particles, aerosol, up to 4 days from now. So this is, again, how it works, and again, in near real time. So Sentinel-3, if you come to visit us, right now you can't because of this COVID situation, but I hope on next year you can. You will see the building of Sentinel-3 on the left, and at the entrance on the right, you will see Sentinel-3, or actually more replica of Sentinel-3, which is in a real size. So this is really how big and how Sentinel-3 looks like. So Sentinel-3, it's a Copernicus satellite, which is originally designed for marine and land purposes, meaning to look at the vegetation, to look at how healthy are our oceans, or things like that. Sentinel-3 has 4 instruments. In blue are the instruments dedicated to the ocean. I'm not going to talk about them today. But in red, you have the 2 instruments, which are not only useful for marine and land, but also for atmospheric. And there will be the focus of today. Just to say that actually Sentinel-3, it's more than 1 satellite. We actually have 2 satellites flying today. We call them Sentinel-3 A and B. Not very original, but it's a way to look at the models. And they fly together since 2018. So it's basically today a constellation, an operational constellation. Sorry, it doesn't move. Okay. So I told you we have 2 main instruments for, among other things, atmospheric purposes. These instruments are called OCHI on the left and SLSTR on the right. These are optical instruments, meaning that they look at the sunlight reflected by Earth at different frequencies. And they do that with very high spatial resolution. OCHI, this is the left. It's basically a merge of 5 cameras. And the spatial resolution of OCHI is about 300 meters. And the funny thing of OCHI is that it's slightly, you can see, tilted to the west, just to minimize some sun reflection over sea. And then on the right, you have what we call SLSTR. The main difference between OCHI and SLSTR is that SLSTR, it's a dual view. What does it mean? It means that if you take a target on Earth, SLSTR sees this target twice in 2 or 3 minutes. So once it will see this target straight down to the point, and 2 minutes later, it will look again at this target, but with a very tilted angle. That's the main specificity of SLSTR. And in terms of wavelengths, so for those who don't know the wavelengths, we can call them colors. They look together, OCHI and SLSTR, at complementary colors. So basically, we look from the very blue, the dark blue, to the green, to the yellow, and then to the red. And to the red, what is really interesting with SLSTR is that we go to what we call the thermal infrared. And that's really important because with the thermal infrared, we can measure and see the fires. That's thanks to the thermal infrared channels that we count the fires, while the channels or the wavelengths more in the green, yellow, are used with the dual view system to measure the aerosol, to count how many particles are released in the air because of fires. Is it moving? Yeah, just to say that, as I said, Sentinel-3 has a shared responsibility between EUMETSAT and ESA. So the level 1, what we call the level 1, it's basically the measurements. It's jointly operated by both agencies, EUMETSAT and ESA. Then if you go more toward the application, what we call between us level 2, the marine applications are fully operated by EUMETSAT. If you are interested by land application, this is operated by ESA. And then regarding the atmospheric application, at EUMETSAT, we are in charge of the NRT, so near real-time atmospheric applications like aerosols, fires. But also if you are interested in the future, I could talk about clouds, water vapor, and many things. Okay, now, what are these fire data from Sentinel-3 and how do we measure them? So, a bit of physics, if you don't mind. To measure fires, basically, we look at the temperatures on Earth, or more specifically, we look at the temperature anomalies on Earth. If you are a hot target suddenly at the surface, whether this is a fire or something else, this hot target will create a strong signal like this peak here. And we have specific channels on SLSTR, Sentinel-3, to catch this peak. So these channels are either what we call F1, S6, S5 here. It's basically between a 2 and 4 micrometers. The tricky thing is that the peak is depending on the temperature. So if you have a target with, let's say, 1000 Kelvin, it's already warm, but it's not super warm. So the peak will be appearing somewhere between 2 and 4 micrometers. So here in the right. And we will catch it with mostly what we call the S7/F1 channel. If we fly over a much hotter fire, like in green or blue, so something that is going much beyond than 1000 Kelvin, then we are lucky because the peak is moving to the left, but we have enough channels on SLSTR to catch the signal. So this is in the short-wave infrared. So it's all about looking at temperature anomalies and then finding the right channel to use depending on the fire temperature, not only to count the number of fires, but also to estimate the strength of this fire. An example, Australia. So you all have heard that Australia has been burning a lot from last December to end of January. This is a typical picture from OCHI, so you can see the clouds, but in the middle here you can see all the smoke. We can guess more or less where are the fire sources, and then all the smoke was spread over the Pacific Ocean. Then we use the different channels from SLSTR. So firstly, if I look at the F1 channel around 3-4 micrometer, you can see that very quickly the temperature anomalies are very well captured, and by the sensor. So in the red are the very, very anomaly hot targets, and these are the fires where they were burning. We could also see them with much shorter wavelengths with what we call the S5 or S6. So here this is an example with S6. It was by night, so the background is in black. And then the fires were also burning in yellowish, almost white. So very strong intensity shared between thermal infrared and more visible wavelengths. And also we could look at the difference between the very long wavelengths and the shorter wavelengths. So this is what I did on the right. And again, the fires appear very well. The clouds also, like at the bottom, appear, but thanks to the other channels, we can distinguish what is really coming from fires and what is really coming from clouds. We can do that also because SLSTR has a very small pixel, about 500 meters. And we are flying early in the morning and early in the evening, so we can see these fires twice in a day, around 10 o'clock in the morning and 10 o'clock, 10 p.m. in the evening. Then we have many information about this product. So what I would like is that I would like to invite you to have a look to this website. This is a website describing the whole algorithm of the Copernicus Sentinel-3 near real-time fire product. So FRP means fire radiative power. So here, this is a website. The overall algorithm about what I described to catch the fires, to count them, and then to estimate the magnitude of the fires was designed by our colleagues from UK, so more specifically by King's College London. Then at EUMETSAT, we used a first version of the operational processor, but we tuned it and did a lot of additional developments. This led us to the processor version number 2. That's the one currently that is running in operational. And today, the first product that we released just a few months ago, it's a baseline collection 1. With the additional work that we did, we managed to reduce a lot of false alarms, especially over water and in the very high north latitude. So that's really important because we wanted to be able to provide you with relevant observations in Siberia. And we are also reprocessing data to support CAMS development. Currently, the version of this product is preliminary operational. The quality is overall very good, but the validation needs to be extending. I will show you a few plots. This is mostly applicable during nighttime, not yet the daytime. The daytime will be ready for next March. There are many parameters in this product that Julia will show you. The main parameters are 2 types of fires, what we call the fire muir, so the fire for which temperatures, I missed 10, are around 1010 kelvins. And for very, very hot fires, and we have another parameter, this is the short-wave infrared. This is for fire temperature, which are going much beyond than 1000 Kelvin. And of course, you have many quality flags featuring that are mostly recommended if you're a little bit expert to guide you about what kind of confidence you can have in these fires. The spatial resolution is 1 kilometer, and we did an upgrade last July to remove some twilight artifacts in the very high latitudes. Some illustration. So this is the fires we could monitor this summer. So on the left, it was the Amazonia, well, not only Amazonia and other forests in Brazil. That was middle of August. We managed to monitor overall the whole summer, and all the pictures are available on the website displayed at the bottom, which is METIS EUMETSAT website. This is public free. You just have to click and you look at the maps. We also detected and monitor a very specific situation in Europe. I don't know if you heard about this, but Chernobyl. Chernobyl has a small fire, but also is famous in Europe because there was a nuclear incident last year. And there was a fire around it. So we just monitored the situation. Luckily, it was not too serious, but it was important to monitor it for the emergency rescue reserve. Australia, so as I said, Australia has been burning a lot last December and January. So this is the typical fires that we could monitor. Most of the fires detected with Sentinel-3 were, of course, along the eastern coast and were very strong, more than 4,000 megawatts. There were also a few fires at the north and hotspots on the left, but these were much weaker, although still persisting at that time. And other fires over Croatia and Balkans, which occurred at the beginning, were more at the end of spring. So the Balkans, for those who don't know it, it's South Europe, close to Croatia. Of course, there is not only Sentinel-3 providing fire observation, so the question is to understand how Sentinel-3 is going to fit with the overall constellation of fire satellites. Currently, the reference fire observations are provided by our American colleagues via an instrument that we call MODIS, which is present on 2 satellites. That has been until today still the main reference fire project. But MODIS is very old and it's not going to last. So right now, NASA is providing another instrument, VIRS, but this is only observing fires in the afternoon and middle of the night. So basically, Sentinel-3 will be incorporated to take over MODIS by looking at fires in the morning and in the beginning of evening. Together, Sentinel-3 and VIRS will be the new generation forthcoming of fire constellation over the world. So to be prepared for this kind of fire constellation, we have to compare how Sentinel-3 is performing with respect to MODIS. We are intercomparing that with a lot of colleagues. Here, this is an illustration. Overall, the main conclusion is that if you compare SLSTR fire on the top and MODIS at the bottom, for all the strong fires, we find them commonly all together. And that's very good. And the magnitude of the power of these fires is quite comparable. So that's a very good sign. The specific thing with Sentinel-3 is that we find more what we call small fires. So meaning fires with low power. It's potentially a very good thing because you have an illustration on the left with the gray pictures. You can see in white strong fires ongoing. It was in Canada. And MODIS does not detect the whole fires. It only detects a couple of these pixels, while with Sentinel-3, we could detect most of these fires. It's very likely related, but we're still analyzing that to the fact that with Sentinel-3, we have a detectability, which is slightly better than MODIS. So all of this is under confirmation, but we do expect we have the potential to better detect in the next years small fires in addition to very strong fires. With my colleague, Andrea Meana, an early career scientist, we are also comparing the Sentinel-3 fires with geostationary. So geostationary, these are the sensors that turn with the Earth and always look at the same face or same side of the Earth. And at EUMETSAT, we have an important geostationary program, which is named METEOSAT. Right now, this is the 2nd generation. Soon we will have the 3rd generation. And our partners from the LANDSAF, the Land Satellite Application Facility, derive a fire product from METEOSAT with a very high temporal frequency. I think it's every 10 or 15 minutes. So you have here over mostly Africa, Central and South Africa, the high temporal frequency of these fires. We are evaluating what we are able to find in common between METEOSAT and Sentinel-3. And here, this is an illustration of what Andrea did lately. What we found out, this is mostly these blue and green pixels, is that if you look at the green, we have more than 80% of the strong fires that are very common between METEOSAT and Sentinel-3. That's very good. It means that between geostationary and Sentinel-3, we are very consistent for the strong fires, meaning for fires with more than 10 megawatts. However, also with METEOSAT, we confirm that Sentinel-3 finds more small fires. So in that case, it means with power less than 10 megawatts. With METEOSAT, that's expected because the size, the pixel size of METEOSAT is relatively big, so the small fires will be quite small. So we are checking that, and we are mostly focusing on small fires. We are deploying this towards an occasional monitoring system, which should be publicly visible for all of you if you wish at the end of the year. And finally, because we talk a lot about fires, but on Earth, you do not only have fires burning, but you have also these industrial gas flarings. So these industrial gas flarings have at the tip sort of flammable gas that burns a lot and is extremely hot. And these have a lot of consequences on the air quality. We know it releases a lot of black carbon particles, which have impact on the surface, but also it contributes to climate because it releases a huge amount of CO2 as the main greenhouse gas. So it is important to be able to find these gas flares and to monitor them in terms of activity. So we do see them with Sentinel-3. On the right, you have a nighttime picture. So basically you see the lights shining by night. This is from the American VIRS instrument. And I hope you are able to see in red on the right. In red, these are the gas flares that were confirmed by NASA from VIRS. And on the left, these were the industrial gas flares that we EUMETSAT detected in near real time with Sentinel-3 based on the FRP shortwave infrared. And so you can see that basically most of these square pixels on the left correlate with industrial gas flares here. So this is in the Persian Gulf, close to Iraq, Saudi Arabia, and so on. And so we could estimate the strength of these industrial gas flares, which is important to predict the amount of particles and CO2 or carbon monoxide being released for them. Again, you can see many more plots, many more maps if you wish on the METIS website, which address is given here at the bottom. Okay, so now I'm going to move about the Copernicus Sentinel-3 near real-time aerosol data. So these air pollution data, which are mostly, but not only related to this fire data, whether this is for last summer or anything else. So aerosol from space in a nutshell. Aerosol, as I said, this is very tiny particles that fly in the air. You have some illustration at the bottom. I hope you can still hear me. I see someone who doesn't hear anything. Okay. So at the bottom, you have three pictures from Sentinel-3. On the left, this is mostly dust flying from Sahara over the ocean. In the middle, this is some smoke, which comes from some fires from Croatia. And on the right, this is a huge smoke coming from California fires. And of course, with your eyes, you can see these particles, but it's also actually a little bit difficult because you do not only see aerosols, you also see what is lying below it, underneath it. And so the tricky thing from satellite measurements, when we want to count how many aerosol particles are present, is that we get the signal and we want to decouple the signal coming from aerosols and the signal coming from the surface. So to do that, it involves a lot of processing, a lot of brains, and a lot of mechanisms, physics mechanisms to decouple what is coming from aerosol, what is coming from the surface, and that's overall the highest challenge. So there are two ways to do that, and with Sentinel-3, what we do at EUMETSAT is that we combine surface information that come from external data. For example, we use wind speed forecast over ocean. We use information that we have from some database about the type of vegetation that is present over land. But also, with SLSTR, we can exploit a little bit further these measurements because, as I told you, we have a sort of multi-viewing, a dual view system. We see the same target twice. By combining this multi-viewing with the spectral signatures, we can also further exploit this kind of measurement to decouple aerosol and surface. In the future with EUMETSAT, we will be able to further do that because right now we have two views with SLSTR, but in the future we will have even more powerful instruments like what we call 3MI. So we'll have 13 views in addition to the two views from Sentinel-3. So no doubt that the challenge will become easier and easier. And at the end, what we deduce, this is the concentration of particles. We call this AOD, Aerosol Optical Depth. It's a spectral parameter which varies so as a function of wavelength. It's basically a proxy of aerosol amount. The higher is the AOD, the more particles you have in the air. So here, this is just some details about the processors, the algorithms that we deployed. I'm not going to detail all of it, but I just want to insist at EUMETSAT, we did a lot of work to improve the spectral calibration of the instrument, which was important for deriving AOD. Then we worked a lot to find out how to decouple the surface signal and the aerosol signal. There are different strategies that are implemented. It depends overall on the type of surface that we have. So if we are over ocean, we use some external data like wind speed. If we are over land, it overall depends on which part of land we measure and whether we can use a dual view system or if we combine that with external data. And then we have applied specific weights, spectral channel weights, to focus on the channels that are the most sensitive to aerosol information. On top of that, we provide in the product information to filter out clouds, to filter out sediments, which perturb your signal, and also statistics about the cloud fraction to be sure that you have at the end aerosol information and not cloud information. If you are interested, you can have a look and read all details on this webpage where we described all these functionalities. We also published a specific peer-reviewed paper, which is here in the top right, how the geometry of acquisition impacts the aerosol retrieval. It's a paper that we wrote with my team manager, Bertrand Fournier. So today is the release status. So this is a very, very, very new product, which has been released only last August. So about one month and a half ago. That's the first release. It's directly from a processor version 2, baseline collection 1. It's available to all of you publicly since end of August. The product has specific maturity levels, which you have please to keep in mind when you use these products. Over ocean surfaces, we consider the product to be preliminary operational. It means that the product is very good, close to the usual requirements, but we are extending the validation. Over land, the product is good for mapping purposes, quality-wise, but we know we still have some uncertainties that we need to tune. So the product has a maturity of demonstrational. Keep that in mind, please, if you use this product. Again, all of this is explained on the website on the right, and in various documentation you can find on this website. The key parameters that Julia will show you, this is the AOD at 550 nanometer. So as I say, AOD, optical depth, how many particles are in the air. We usually give it at 550 nanometer because this is a well-known standard wavelength reference in the whole aerosol community. If you're not expert in aerosol, just to use this parameter, that's it. If you are more curious, and of course I strongly encourage you to be very curious, you can look at the other parameters which give you information about aerosol properties, surface properties, quality flags, etc. This is an animation of the aerosol measured by Sentinel-3 over California. So you know, last September, so not even 1 month ago, California has been burning a lot. So the fires were mostly over the western coast. And the fires were so strong and so much persisting over more than a month, that it released a huge amount of smoke that has spread over the whole North American continent. And it was confirmed with our own aerosol product from these fires. But also, interestingly, this smoke was released over oceans. So there was a huge plume released over Pacific on the western part, but also over the Atlantic. And actually, you can see that the smoke has been flying from California to the eastern part of the US. Then it even went further over the Atlantic. And it actually, we know that it reached Europe. Some of our colleagues in Germany have measured smoke coming from California over Tropos, but also over Darmstadt and so on. So it's really unbelievable that with Sentinel-3 and other satellite and sensors, we could see that the plume has traveled I don't know, more than 10,000 kilometers in a couple of days this summer because of fires. Some just words to tell you about the quality of this product. So as I told you, over ocean, we are really good. Again, we have to see how Sentinel-3 is getting integrated in the constellation with the other existing satellite sensors like MODIS. So over ocean, overall, we have excellent consistency. This is what you can see on the left. We have almost a one-to-one line between SLSTR and MODIS Aerosol Optical Depth. We know that with Sentinel-3, the AOD is slightly lower, and our partners overall see that with a good eye, because it seems to be confirmed that MODIS has a minor bias over ocean. So we are trying to confirm this, but we are lower by minus 0.01, 0.02, so something quite acceptable. And you have an illustration of the typical AOD over ocean from Sentinel-3 on the right for a given day. We also validate the product with ground-based measurements. So for that, we use what we call Aeronet. So it's basically sun photometers, ground-based. And yet again, there over ocean, we find out the correlation is very good, up to 0.77 something. And the deviation is quite low, about minus 0.02. We have some dispersion in case of high AOD, but nothing to be worried, because it seems to be more related to some artifact due to coastlines. We also evaluate the product over land. So as I told you, it's less good than over ocean, but still very good. Here, this is a comparison with MODIS over India during the agricultural burning season. So the overall both products are very consistent and show almost very similar patterns. We just have a few cloud residuals on southeast over India, but otherwise everything doing very good. And again, we compared also with ground-based measurements with Aeronet. So with Aeronet, we have something quite good overall, a correlation of 0.7. We have some dispersion, so we know that we are analyzing this. What is quite well known, and you need to keep that in mind, that we have a small bias in case of low AOD. So that's why for now, the quality label is demonstrational. I'm not going to spend time to explain this, but we know the reason of this bias, and it's under correction for next spring. Okay, and now at the end, what we have, it's both. We have fire products, we have aerosol products, so we can monitor. Oh, I'm sorry, the date is overlapped by the gray box. So we can now monitor at both products, fire and aerosol, all together, and that's the case during Siberia wildfire last June and July. So you probably heard that Siberia has been burning a lot because it was very hot, very dry. So the amount of fires was huge, about 10,000 fires, if I'm not 5,000 fires, if I'm not wrong. And what is really interesting is that if you look carefully, the fires have started on the eastern part of Siberia, the first days, and then slowly it moved to central and left part. And if you look at the aerosol smoke that we got from Sentinel-3, it follows the same pattern. The usual red smoke started on the right, and then slowly they move to the center and to the left. So overall, it provides really a lot of information. You have fires, you have the impact of fires on the air that people breathe every day. You can see a lot of correlations, so then you can anticipate from forecast point of view, emergency point of view, how it's gonna affect people, or whether it's not gonna affect because the fires may be contained in some remote natural area. Okay, so the last part of my talk, where can you find the data and how can you visualize them? So all these data access and documentation are available on the EUMETSAT website. The address is here at the top. You don't need to write it. You will have my slides at the end. This website, this is the EUMETSAT website dedicated to the list of near real-time NRT atmospheric products of fires, aerosols, and many others that we EUMETSAT derive from Sentinel-3. If you click there, you will find a lot of documents describing the product format, how to use them, the quality labels that I told you. I strongly encourage you to read at least what we call the product notices, because there you have all the details about the good quality, the validation status, but also the non-limitation of each of these products. If you have any questions, you can contact my colleagues at ops@eumetsat.int, and I will help you. From this website, then you have a lot of links to where to find the data. One of these links, this is what we call METIS. METIS stands for Monitoring and Evaluation of Thematic Information from Space. This is a public and free website from which you can visualize directly the projects. So if you don't want to download the project, but just look at them, just go to METIS. Currently, the fires product from Sentinel-3 is there, and soon there will be the NRT aerosol product. So if you go to METIS, you have the fire at the bottom. If you click on it, then you go to the main page of the near real-time Sentinel-3 fire product. You have some explanation about the product, some maps. Then you can click on these maps, either the left or the right. On the left, in that case, this is Sentinel-3A, the first satellite. On the right, this is Sentinel-3B, the second satellite. And if you click, well, you can see this map. So this is the FRP wheel for fires at the temperature of 1000 Kelvin. You can also click on the right to either zoom on a specific region, change a satellite, or visualize different parameters. And at the bottom, you can look at different dates. If you want to download the product, you can go to the CODA website, which is a Copernicus EUMETSAT data access. You just have to register, you give your name, your email address, and then you can look at the list of data. And there, I put the red circle, you have SL2 FRP, that's the near real-time fire product, and SL2 AOD, that's the near real-time aerosol product. All of them from last summer 2020 are there. If you click on FRP, for example, you will see that. So on the right, you will see where the granules are present over Earth for a given day that you specified. And on the left, you can find some help in case you want to download a specific granule with or without fibers. Okay, so on CODA, you mostly have products which are available for the last year, so within a 1 year time frame. If you want much older product, then you have another access that is available, which is the EUMETSAT data center or the archive EUMETSAT. So same, you just click on it, you register, and then you can have access to the data. And the data are available in the list. I surrounded with this red circle for you. SLSTR level 2 aerosol optical depth, so the pollution in near real time from Sentinel-3, and just below the fire product in near real time from Sentinel-3. Here, this is a summary of all the links. So if you are interested about the fire algorithm, all the details are there. If you are interested about the near real-time aerosol algorithm, same, you have all the details on this specific web page. These web pages will be updated about twice or even 3 times a year, depending on the evolutions. The list of all the near real-time atmospheric projects with all documentation on how to get access to this data, this is on the EUMETSAT web page. Please, again, take some time at least to read the product notices where you have all the non-limitation caveats and non-qualities. If you want to see directly the product, go to the METIS website for the public visualization. And then if you want to download data, you can go either to CODA or the archive data access. And if you have any troubles, of course, you can contact me, but I think it's better you contact directly the EUMETSAT help desk. My last slide. So Sentinel-3, it's a European-funded operational marine and land mission. And today it has become an atmospheric mission with great interest for fire and air quality applications. At EUMETSAT, we're in charge of the near real-time product, near real-time fire, near real-time aerosol, and with them, we could monitor the summer 2020 fires. I showed you many examples, but you have many more available on the website that I show you. We are responsible to maintain this product for the European Commission, and we are preparing the next evolution for next spring. Unfortunately, no doubt that there will be still some fires ongoing between now and next spring, so we will monitor them. And my colleagues, such as Federico and myself, will keep you posted about this. That's my email address, and if you are interested, sometimes I post some of this information on Twitter. And with that, that's it, and I thank you very much for your attention.
Okay, thank you very much, Julien. That was absolutely great. We have a few questions on the Slido. If you wish, I can put it up here.
Yes, you take over. Super.
Yeah. Okay. So I mean, there were two questions on the chat that I have put here from Bezuz. So the first one is, how effective are the hot currents on the surface of the Earth in forest fire? I mean, I think we are talking here about pyroconvection and about this type of. Yeah, I guess. Yeah.
I guess, yeah, because currents. Well, it depends overall on the. So I'm not a big expert about how fires are triggered, but I guess it overall depends on the meteorologic conditions and the moisture and the type of fuel, whether these are trees, moist trees, dry trees, and so on. What I can say is that, of course, when you have fire, you have a lot of smoke and you have a lot of clouds, so it's not easy. But luckily, with Sentinel-3, we have thermal infrared channels. So in general, smoke is not a problem. We always see the fires through the smoke. So then we can always see the surface burning, whether these are forest fires, savanna, or hotspots. Of course, if we have thick clouds, then yeah, the fire will be hidden. And that's the main limitation for any satellite fire observation.
Yeah. I mean, I imagine that the question is more on the effect of fires on circulation. So, but I mean, just to add one point is, I mean, pyroconvection is a phenomenon that happens in the most intense fires. I mean, because the fire themselves, I mean, the fire are very hot, and then you generate a strong temperature gradient in the atmosphere, and then you generate convection itself. And for instance, in the case of the California fires, there was one of the huge event on a pyroconvection. I will post on the chat the link so that you can read more on this. And for instance, pyroconvection is important to project on a higher altitude the production of fires, and this happens in higher latitudes where the ground surface is colder, and then the effect of convection is more effective in generating convective clouds.
So for sure, the smoke that has traveled from California to Europe was injected very, very high in the troposphere, about 5 kilometers, I think. And that's why it could travel that far from California to fire. It has to be very high in the atmosphere.
No, it was even higher. I mean, the measurement of Calliope, that is the LiDAR that is on board, reported that the California fires of 2020 were up to 14 to 15 kilometer height. So, and also the Australian fires in 2019, 2020 were very high. So again, some of them even overshooted the stratosphere. So. and entered the 16th.
Australia was completely overshooting in the stratosphere, and the Calliope saw a big bulk of smoke being stuck over the Pacific, close to the South American coast, and it was stuck for at least 10 days, I think.
Yeah, exactly. I mean, I think we can, okay. While you answer to the second question, that is, can satellite help predict widespread fires and which areas? I just provide some image on that.
Yeah, so yes, it can, although we're not the ones doing that. So at EUMETSAT, we are the ones processing and interpreting the satellite data in terms of observations. But then I mentioned the CAMS, the Copernicus Atmospheric Monitoring Service, and they are the ones to take our data and then to combine them with their own models. So we call that assimilating, in order to predict, forecast the potential damages of these fires in the next hours, in the next days. And they do that twofold. They, of course, try to predict where these fires are going to move. So they look at the wind, they look at the meteorologic conditions, but they also look at how and where the smoke will move. And for sure, they need any observations, and satellite observations are one of the main inputs.
Okay, and I think this question also support, do you use Sentinel-3 and RT data in fire and particulate matter forecasting models? Do
So
you?
CAMS.
CAMS, okay.
Not us at EUMETSAT. At least I don't think so, because at EUMETSAT, we are the ones processing satellite data, but we work very closely with CAMS and you too as well, Federico, because they want to use this data with the models to predict what you ask for.
Okay. I mean, I just go back to the question of the pyroconvection, and here is a recent science story that we have published on the EUMETSAT science blog, that you can find it here on scienceblog.eumetsat.int. And in fact, the satellite observation they show, and that this is from METOP, so is the channels that we use for high convection, and you see that a very high convective cloud and the plume topping out from it. Mm-hmm. And that this was also described by NASA, and here is the story from NASA. You can see it here. I mean, it was very intense, and I think that this is probably.
Yeah, it's basically an explosion, no?
Yeah, exactly. It is very intense convection, very deep convection. Okay. Another question: up to which latitude can SLSTR provide reliable observations? Being a polar, huh?
So. So in theory, we provide up to the very north. There are no doubts about this. I don't have yet an ultimate number to give you. What I can say lately, thanks to my colleagues from Norway, there was an industrial explosion end of September at the very north of Norway. So I don't know which latitude it is exactly, but it's 80, 82 degrees, something like that. By night, it was an industrial explosion, and we detected it. We saw it, we detected it, and the FRP, the radiative power, was qualitatively reasonable. So it gives me a strong feeling that we may detect fires, at least industrial one, up to 80, 82 degrees. Now we need to finish the validation in very north latitude such that I could give you a clear number.
Okay, great. And there are, probably we can, I can provide you with the last question, and then the second one. So what is the probability of detection for industrial gas flares with the near infrared channels? Because you have started to, you have mentioned the flare in Norway, and then
exactly. So in terms of probability, at least 80%, but for sure not more. What I can say is that if the flare burns more than 3 megawatt from a radiative power point of view, we do detect it with a short range infrared. So the detectability is about 3 megawatt with SLSTR. I know that over Algeria and Tunisia, we detect them very well. We are close to 100%. Over Persian Gulf, over land, we detect most of them. The only difficulty that we have now, this is a very narrow water basin, the Persian Sea, I think it's called, which is very narrow, and you have a few gas flares right in the middle. And for this one, we have a few difficulties there. That's it.
Okay, and the last question of this round is about the, I think, recovery. I think I imagine that is the retrieval. So how are Sentinel-3 Aerosol Optical Depth retrieval different from the MODIS?
Well, we could discuss for how long do I have?
No. You should be synthetic.
So firstly, the main difference, this is from instrument point of view. MODIS, it's what we call a monoviewing. So the main, if you take a target on Earth, the target is only seen once by MODIS. With SLSTR, as I said, this is a dual view, so we saw twice the same target. So the instrument is already different, which means that when we want to decouple aerosol and surface, we use different instrument techniques already. So there is a big difference from instrument. Then from algorithm point of view, MODIS mostly estimate the surface from external data. They don't do a joint aerosol and surface retrieval together. On SLSTR, we do something a little bit hybrid. Sometimes we use external data. Sometimes we use we jointly retrieve aerosol and surface. As I said, it depends on the surface type, the geometry, where we are on Earth, things like that. So at very high level, these are the main differences. If you want to know more, I don't know who this is, please read the webpage that I show and potentially contact me and we can talk more in more technical details.
Okay, okay, thank you very much, Julien. I mean, it's a great discussion. So if there are not additional questions, I just check one moment on the chat, but okay, I don't see. So we move to the data discovery with Julia Wagaman from MIO, that is a business company that is supporting and works since years in data analysis, in data diffusion, and so on satellite, and is also supporting EUMETSAT as a contractor. And I will leave the floor to Julia on the data discovery using the Jupyter notebook. Okay, the floor is yours, and I mean, take the time you need. We are just eager to hear you.
Thank you, Federico, and also a warm welcome from my side to everyone. I just start sharing my screen. Okay, good. So, and also thank you to Julien for giving this great introduction to the data. And I will now give you the next 25 minutes. I will give you a short introduction into how you can actually use the data Julien presented. So he gave a lot of theoretical background, how the data is produced and how you can also interpret the data. And I will show you once you download the data, where you can also download them. Julien already showed you. And once you have downloaded data, how you can make use of the data and how you can retrieve fire information. All the information, how you can access the training portal is also on the Moodle webpage. And we also send you already the information in the emails. So in case you haven't registered yet, you can go to this Moodle page. You should see on my screen here. And there is a Jupyter Hub instruction, how you can access the Jupyter Hub, which is the training platform with all the training material available. And so the web address is ltpy.adamplatform.eu. And in order to access this web address, we ask you to create an account under this web URL. And once you created an account, you can log into the Jupyter Hub. I just want to inform you that there is a maximum of 100 places available, and places are given on a first come, first served basis. So if you would like to take advantage of the practical training material, I recommend you to register on the platform. How it looks like, so if you go to the registration page, it looks like this. And if you're new, you don't have an account yet, you just simply go to register, you enter your information, and you will receive an email to confirm your email address, and then your username and password is accepted. And then you can log in, and then you will get a link to the LTPY platform. And if you enter the LTPY platform, it looks like this. So this is basically an overview of different Jupyter notebooks and different training material you can make use of. So for those who have not worked with Jupyter notebooks, it's in principle a environment, like a training environment where you can work and also try out the code we provide you, and you just make the changes for your image. So basically, once you log in, you get a fresh training environment, which helps you to really practice also the content we provide you. So an overview of what is here is basically we have different folders. The important folder for you is EO data, where all the data that is available for the training is stored. And also, this is a folder for further information, which contains a collection of notebooks related to atmospheric composition data in general. So not only fires, but in general data on air quality. And we also invite you to have a look there. For this session and also for today and until Monday, we prepared these 1, 2, 3, 4, 5, 6 notebooks. And if you go and you start with the notebook 00_index, and this notebook just gives you an overview of what it contains. Also, again, a reminder on how the course is structured. So today is the short course, and on Monday we have a short course feedback session. So this is now from today until Monday is really also your time to train practically with the data, and then on Monday we come back. There will be Julien, there will be Federico, there will be myself, and any questions related to the data and the products you can then ask again to us. For the training, we developed a set of 4 notebooks. So 2 notebooks showcase you the workflows. So basically how you get data from, like how you load the data, how is the data structured, and up to how you can visualize data. And these examples are based on an example of the Californian fires that just recently happened in August. And these 2 workflows showcase the 2 products Julien introduced. So the first product is the Sentinel-3 near real-time SLSTR fire radiative power product, and the second one is the Sentinel-3 near real-time SLSTR aerosol optical depth. And for both products, we also developed exercises on different fire events. So the near real-time, for the exercise on the near real-time SLSTR fire radiative power is based on Siberian fires that happened in June this year. And the example for aerosol optical depth is based on Australian fires that happened last December 2019. And so the exercises are really a good way for you to practice, because we ask you some questions on the data, and this is also your chance to enter code and to really play around with the code we introduce in the workflows. Just before we start, there is additional notebook available. It's called 01_Introduction to Python and Jupyter. And in case you don't have a lot of experience with Python and Jupyter notebooks in general, this is your notebook you can start with. So it introduces you to the Jupyter environment in general, and also gives you some examples how you can interact with Jupyter notebooks in order to make the best use of this learning experience. And then I will start with the first workflow on Sentinel-3 near real-time SLSTR fire radiative power product or example. And this example is based on the Californian fires. For the FRP data, we chose an example which is based on 12th of September 2020. And as Julien already also showed, this is a red, green, blue composite of Sentinel-OLG level 1 data for the same day on 12th of September 2020. It has the bounding box of California, and you see like smoke over this part. And so basically we now, in this workflow, we showcase you how we can make use of the fire radiative power product in order to identify how many fires were there on the same day. The workflow has 4 different parts. The first is to load the Sentinel-3 near real-time SLSTR FRP data. Then, as Julien introduced, is that the data provides data or variables on different channels, and these channels are depending on on the fire thresholds, or no, on the temperature thresholds or temperature anomalies. And so we will also go through the 3 examples you can make use of to detect fires different based on different temperature thresholds. And so each workflow starts with loading a couple of libraries which you use for plotting and also for analyzing data. All the examples here, they heavily based or make use of the Python library called xarray, and also to visualize the data, we make use of matplotlib. The workflow is also based on a set of helper functions. And so we basically, for each workflow, we introduce the functions, and we also showcase you what this function contains. But all the functions, they also part of an additional notebook called functions, because we can make use of these functions again. And so for this example, from the functions notebook, we load specific functions that are available in order to generate a masked array, in order to visualize the data, and also in order to grid the data onto a regular grid. So basically the near real-time SLSTR FRP data is disseminated in netcdf, and the first step is to load the data, and we can load data with the Python library xarray, and it has a function, it's called open_dataset. And this is quite easy. So the data is in the EO data folder under Sentinel-3 and then FRP, which is for fire radiative product. And then we want to load the example for California on 12th of September 2020. And if we do this, we get a xarray data set. And this data set contains different type of variables. As Julien already said, it provides different types based on temperature anomalies and channels. And this is the data, this is the variables the data set contains. So we have fire radiative power on the MIR channel, but also fire radiative power on the SWIR channel. And also here, this is some flags for anomaly, to include some anomalies to the data. And so you can have a look there. We will make use specifically of FRP MWIR data and also of the SWIR channel today. And so once you loaded the data, we have the data set, and we can now load specific data variables. And so in order to do this, we can just specify in square brackets the data variable we're interested in. And so this example, because latitude and longitude information we need in order to understand what bounding box or what geographical area the data covers. And so we can load the data with square brackets and identifying the name of the data variable. So this is FRP, so the data set, and then we load latitude and longitude information. We also additionally, we define different variables for plotting and gridding, which helps us to bring the data, to define the regular grid we want to have the fire information on, and also the latitude and longitude minimum and maximum information in order to visualize it later. So here we define a bounding box for a bit larger than California. And we also want to bring it onto a 0.05 degrees grid. So now we go through the 3 different variables, what I said before, and we load the variables, we mask them, we regrid them, so we bring them onto a regular grid, and then we visualize them. And for time purposes, I will go through the first 2 examples, but basically the workflow here is just the same. So for each data variable, if it for each different channel, it's the same workflow. And I think you can have a look later on or tomorrow or next days in order to go through this third example. And then I will go to the aerosol optical depth. So we do the same. So what we did for latitude and longitude information, we do the same for the data variable, which contains the information for the fire radiative power information from the MIR channel, which is from S7 and F1 channel, which is below 1100 Kelvin, so which detects fire below 1100 Kelvin. And so we load it also again with square brackets, and then we see, so from our data set, we now loaded a data array with this specific variable, and we see here that it contains 983 fire information. Good, and we also see some attributes like the units and also the long name of our data array. So the next step is then to extract only the right fire radiative power pixels. And valid pixels are all pixels that are different to -1. And for this, we can use the function generate masked array, which you also see in the functions notebook in order to extract the right pixels. And so we use this function here, generate mask array. We specify the array, or the data array we loaded with our fire information. We specify all the pixels which are different to -1, and we also say that all the pixels that are filtered out we don't want to keep, so we want to drop them. And then we see that from 983 we have then just less fire information, and we can now also retrieve the number of hotspots or fire in total and also per category. And this is we can do by getting the length of the number of fires and also the information from the mask array. And here we say here, like we have a total number of fires of 983. And once we mask the data just with the channel information, we have 947 fires. So the next step is now to create a gridded fire radiative product, fire radiative product, so to have it on a regular grid. And so the gridded fire radiative product is the integration or the sum of the fire radiative product within a grid cell. And for this, we define the function which is called SLSTR underscore FRP underscore gridding. And then we can, and once we define this function, we can reuse it again to apply to data variables. And so this function is quite complex because basically you can have a look, and this function, when we also apply it, it takes a bit because it really creates a regular grid for each pixel and also calculates the right number of fires for each grid cell. Yeah, so with this function, you can create a regular grid, and basically we can apply this function, and then this function results into the fire information and also the latitude and longitude information we can use later for plotting. And so if you go through the example, don't worry, this is really the heavy computing which will take place here, and this takes a while in order to regrid the data. So there you have to take a bit of time. So like, yeah, up to 3 or 4 minutes. And then so once we regridded the information, we just want to mask out invalid pixels for plotting. And so all the pixels that are minus 991, we want to remove, and all the others we want to keep. And so once we have a masked array, we can get some summary statistics in order to add this information to the plot, which can be integrated to the plot to have the average, the standard deviation, the minimum and maximum of the data, and also to add a specific title, and also to understand what the data is actually showing. And so, and the last step is then to visualize the data with a function. It's called visualize_S3_FRP. And we use all the variables we defined before. So we have the data, so the fire information regridded, the latitude and longitude information regridded, which we retrieved from the function before, the unit and long name, which we can retrieve from the data file, and the text strings we defined here. And so this is basically just a function which combines matplotlib and cartopy in order to have a nice visualization. And once we have this visualization, this function, we can apply it to our data. We define also long name, units, and also the maximum value we want to visualize. And then we can visualize the information we just retrieved. And so we see that we have a total number of fires of 947, and also some summary statistics of the data. And this is the geographical bounding box of California. And so basically this is now an example how to retrieve the first part. So one channel which has detects fires below 1100 Kelvin. And the next step would be to retrieve a different variable in order to detect also fires that have a higher temperature. And this is from the FRP sphere channel. In order for time, because this is basically the same example, so we just load a different variable. In this case, we load the FRP_sphere variable, and then we do the same steps. So we generate a masked array, we define we also compute a number of total fires and also per category, and then we apply again the function SLSTR, FRP, and gridding in order to bring the data on a regular grid. So I will not go through this example again. We just see here that basically once you retrieve this variable, we have much less fires identified. So this means less fires had a temperature which was higher than 1100 Kelvin. And so out of the 983 total fires detected, 312 fires had a higher temperature compared to 947 fires which were detected through the VIR channel. And so, yeah, I just invite you to go through the example and also to understand the difference between the different channel information. And for this, I go now to the next example, to the Aerosol Optical Depth product. And so you can, so this is basically a sequence. So once you went through this notebook, you can also go to the next notebook. And so we have here the example or we have an example about the Sentinel-3 near real-time SLSTR Aerosol Optical Depth product. And so as Julia said, so the Aerosol Optical Depth is a proxy for the aerosol amount. And here again, the example shows an example from 1st of October 2020, also from California. And you see here also the RGB composite of Sentinel OLG level 1 data on 1st of October. And again, we see here smoke over this area. And so now the example shows how we can make use of the Aerosol Optical Depth data that comes from the Sentinel-3 near real-time SLSTR data. And this is the workflow is how to load data, and also showcases you how the data is structured, then how we can extract the AOD variables, and how we can visualize the two different variables which are based on different maturity levels. So the AOD variable on ocean, and also the AOD variable over land.
Julia, sorry, Federico speaking.
Yes.
There is one quick question, probably of clarification from Luigi Selmi on the chat. So it's about the gridding procedure, so the function SLSTR gridding. The question is, it computes the number of fire on each cell in the grid?
Yes, yes. I think also it would be good, Julia could also bring in, because the function also has been developed from him. So
yes, it computes the total radiative power of each grid cell. It's an integrated FRP. The total number of fire is given thanks to the loop at the end via the statistics shown by Julia. But it gives the total, because what matters, it's not really the total number of fire. You can have a lot of fires, but with small magnitude, or one big fire with high magnitude. So what matters at the end, it's overall how much it is burning. And what we do is that we compute the total FRP per grid cell. That's what it does.
Yeah, since we are here, there is another question still on the, on the technical. So the question is if it is possible to extract data from images, so from arrays, in a specific grid cell and plot them in a time series. So to make a time series over a site, yeah.
Yes. Everything is possible. It depends on how much proficient you are in Python, but of course it is always possible. You select an area, and then we can look at time series every day.
Okay, maybe we can, just before closing, we can probably give a hint on that, Julia, if you wish, and then this may be a sort of homework for the next session.
Yeah. Yes, sure. So we can, so basically the examples don't showcase this yet. So we would need more data, because we would need, I don't know, over a series of some days, we would need the data, and then we need to extract the data from one specific grid cell. But in general, it's just a couple of different steps in order to actually make it, but the basis in order to retrieve to get a gridded information of the fire radiative product is there.
Yeah, but this person, so if she or he wants, can try to download the data via the link that I showed on my talk, and I don't know, can download a couple of days of California. And then using the routine showed by Julia, she or he can plot the FRP for every day. And then we can see the time series. If he or she wants, we can have a feedback about this on Monday.
Yeah, this sounds good as a great exercise. Okay, good. So then I just go over the Aerosol Optical Depth workflow, and then we can continue with the questions. And so basically the data is also disseminated in netcdf, and as before, we can make use of the Python library xarray and the specific function open dataset. And the data file contains 2 dimensions. So once we open it, we have 2 dimensions, columns and rows, and also again a set of different data variables. And this is again something where you can, or we invite you also to play around and to also understand the data better. As Julien said, so the standard proxy for aerosols is usually AOD with 550 nanometers. So this is the standard wavelength that is used, but the data file,
yes. Yeah. So sorry, I just said just to confirm what you said. Sorry.
Okay. But yeah, so the data also contains data on different wavelengths, and so you can. So it's also good just for you to practice and to see also differences with data on different wavelengths. Good. So, yeah, the data file, you see there's quite a few data variables and also again attributes which give you some more information when the data has been processed, who is the data originator, etc. In order to retrieve the aerosol optical depth variables, we interested in two different variables. So we are first interested in the variable AUD_550, which gives us the aerosol optical depth at 550 nanometers. And then we also interested in the aerosol optical depth 550 land experimental post-filtered. And this is the two different variables that have the different maturity levels, what Julia explained. And we can, again here, this is just a different way in order to extract variables, but the same you could retrieve if you use the squared brackets and then the string or the name of the variable. So we retrieve the example, the variable here from the file, and once we retrieve it, we see again that we have two data arrays with rows and columns and some different attributes. So long name, which explains what the data is about, also valid min and valid max information, and also the coordinates. And so so the same what we did for the variable, we can also do with latitude and longitude information, because this is the information we need in order to visualize. And so we do it the same way. We load the latitude information and also the longitude information. And so, this is, so in order to visualize the data is much easier than the FRP product. What Julia also said, in order to actually get to the aerosol optical depth is much more complex to actually retrieve the data, which is being made available. And so basically, once we retrieve the variables and also the longitude and latitude information, we already have the information we need in order to visualize the aerosol optical depth for the specific region we're interested in. And so for visualizing the AUD data, we specify a function, it's called visualize P color mesh, and it visualizes both variables with the different maturity levels, so AUD over ocean and AUD over land, together onto a map. And the function takes different arguments, keyword arguments. So it takes the two variables, the latitude and longitude information, the title of the plot, how you want to call the plot, the unit of the data, the minimum and maximum values in order to visualize the data, also a color scale and a given projection. And again, here, this is the code which for visualizing, so it's a combination of matplotlib and cartopy. And if we then apply this function, we see then the data of aerosol optical depth at 550 nanometers for both variables over ocean and also over land. And for this, I would just showcase you how an exercise, before we close, I would just showcase you how an exercise looks like and how you can make use of the exercises. And for this, you open one of the exercise notebooks, and this is an example of the exercise notebook in order to practice working with the Sentinel-3 near real-time fire radiative power product. And so before you do the exercises in an optimal way, you would have gone through the notebook, which I just introduced which showcases the Californian fires. But the example for this, it showcases the Siberian fires, which happened in June 2020. And so basically how exercise notebooks work is that you have different colored cells. So the cells that are colored in yellow are coding assignments. And this is really the parts where we ask you to to enter code yourself, to really also understand what you do with Python. And then the green colored cells, these are questions. And the questions is basically that make you reflect on what we just retrieved from the data, or we ask you to have a closer look to the variable and ask you to retrieve some specific information. This also makes you reflecting about the data and the different steps that happened. And so the exercise is just based on retrieving or showcasing one example to retrieve the variable for one specific channel, the mirror channel. And each exercise is basically, we give you an introduction and also some hints on how you can, what you can use, what library and also what function. And in the coding assignment, we ask you then, please load this file, which is under this directory, and call it in this way. And then you can enter your solution here. And once you have your solution and you have problems or you have difficulties, then you should try again, but we also offer you a good solution. And so basically, if you're interested in, you can also here open the solution, and then you see the solution, how it could be done. But in Python, there are many different ways how you can actually achieve it, but this is just one example or one solution we provide you. And here is an example of the question. So once you loaded a data set, have a look to the variable you just retrieved and how many dimensions does the data set have, and also what data variables does it contain. So just it makes you reflect on what you just loaded and also about the data set or data file itself. And yeah, with this, I just invite you now to register, to log into the Jupyter Hub. It's really, you're there for you the next days, and yeah, try out the notebooks. And then we meet again on Monday, and any questions in between, post them on Slido, and then we're happy to respond and discuss on Monday. Thank you.
Okay, thank you, Julia. Yeah, probably before going to the last questions that we have, I mean, there is one quick point from Antonio Giovanni Bruno about the exercise notebook on the platform. Antonio says he cannot find it, but it can be maybe troubleshooting for a single, right?
Well, I will make some tests with so if you don't find them, then I'll make sure that we redeploy again. So then I'm sorry, but it should actually be there. If not, we make some tests after the training, and we will make sure that you have it available.
Okay. Okay, then we have a few additional questions before closing. There is a question on the format, on how the data are provided. I gave an answer. So yes, the data for the moment comes out in netcdf, but we are exploring the provision on additional formats. I mean, this depends also on the needs of the user. So please, I mean, provide feedback to ops@eumetsat.int about this type of needs and of requests. I don't know if Julien, if you want to add something about that. But
No, I totally in line with you. netcdf 4 for now, because that's a request that we have from the commission. But we, Federico and I, strongly encourage any users like you, if you have any need about a specific format, especially I think the FRP, please submit your request to ops@eumetsat.int. I can tell you from there, we get the request and then we have quick discussions internally to move on with that.
Yeah, exactly. I mean, the provision of the data also depends on the user needs. And I mean,
it is possible to change the format, but EUMETSAT, we do it only if we have official user requests. So please do it.
Exactly. There is one question on the notebook 12 that shows the example of Siberian fires, but I think that this has been shown on the Californian ones. So we have So this is done. This is done. Okay. This was the question about. This was about the extraction of the time series. Julia, until when they will have access on the account and the training notebooks?
So definitely until Monday, and probably even a bit longer. So this is just to bear in mind, this is a training platform. So once you register, you have your account and you can make use of it for the next month. It's just, the content can change. So we make sure, like, until Monday and even until end of next week, that this content is available. But because we have also following or training events in November, the content or the notebooks that will be available, they might change. So if you're interested in the notebooks, then you can download them, or we also made you available on the Moodle. You can also download the material for the short course.
But so on the website of the course, that I will put it up again in a few seconds, you can find all the information. So how to download the whole notebooks and run them on your computer, right?
Yes, exactly.
Okay,
yeah.
Perfect. Then there is a question on the precipitation. Yes, does precipitation affect the capability of satellite to detect AOD?
Precipitation in itself, no, but if it rains, it means we have clouds, and clouds do affect because they basically shield what is below it, so especially aerosol. What will also affect a bit, this is the presence of water vapor, but the presence of water vapor in terms of signal is very minimal for AOD. So the main issue will be more clouds. If you have a cloud, we cannot see what is below it.
There is an ancillary question on the validation of the data sets. I assume that is not directly connected with the precipitation. So can you just tell us a few words on how do we evaluate an AOD?
Which one, AOD or FRP?
AOD.
AOD, so this is a bit what I showed. The main validation is firstly based on ground-based sensors. So it's mostly what we call Aeronet. It's a worldwide ground-based network, which measures aerosol in the sky every day, almost every minute or so. So we collocate with these ground-based networks. The methodologies are a bit complex because you need to find the closest satellite observation. But once you do that, then yeah, you validate with it. Then for us, it's not enough because we are, there are many satellite pixels that are not matching with the ground-based. So what we do then we intercompare satellites between them, like Sentinel-3 versus MODIS, because we need to understand how we fit to each other. At the end, users do not want Sentinel-3 alone or MODIS alone. They want everything integrated all together. So consistency is important. And at EUMETSAT, so we spend a lot of time to look at the spatial maps, the patterns, whether it makes sense from physics point of view, things like that. So yeah, ground-based integration of the satellites all together and the mapping.
Okay, great. Thanks, Julien, and thanks, Julia. I think we had a 2 hours short course, so it's short, but not so short at the end. So I want to remind you again what has been already mentioned by Julia, so that you can play with the data by yourself, to access the data and to play with the handling tools. You have all the information on the training website, and also, of course, you can make use of the platform, or the Jupyter have a platform. Then we remind you, and you will receive a reminder one day before on the session next Monday on 19th of October. We will be there again to discuss with you. Probably there will be less people, and we will have the possibility to see what you have done and to discuss with you about the handling of the data. You can continue to put on question on Slido, so we'll follow them. We don't grant, of course, the any real time as the file product answer, but we'll make use of them also for the session on the 19th. So, having said that, thanks again, Julia. Thanks again, Julien. I mean, it's a virtual applause for you, and also thanks to Regina Hoffenmeier and Madalena Ungur that have managed the organization of this meeting. And I just give you with the two last points. So the first one is to provide an evaluation, to provide your feedback on the course, that you can provide it with the website and the link that has been provided in the invitation email. So please do so. It is important for us to hear from you. And then I also remind you that the short courses goes along for the next months, almost every 2 weeks, and the next one for which the enrollment is still open is still on burning issues, so is about the insolation dataset, the climate dataset from SARA. So from the climate monitoring satellite application facility from EUMETSAT. So having said that, I thank you very much, and again I hope really to see you soon, and keep safe, and thanks for joining. Thank you very much.
Just one more thing. Sorry to say that
at the moment
we have an evaluation for this session. Please, if you can all go to Slido and fill up answer the questions that we have there for you. We will leave that open for everybody. Thank you.
Okay, thank you, Regina. And
keep safe, everyone, and thank you.
Okay, thank you, Julian. Thank you, Julia.
Thank you. Bye.